So this is the first of 3 videos on how we can choose between different competing linear models. So suppose we have 2 models we want to consider, model A and model B. And we want to say which model is better for some purpose, like making a prediction or doing inference. So the first thing we need to consider is some measure of how accurate the model is. So we're going to talk about something called goodness of fit, and that's a measure of how well the model fits the data. And one of the problems we're going to run into is that more complex models will always fit the data better than simpler models. So we can't just consider goodness of fit alone, we also have to consider how complex the model is. And that's the subject of the next video, where we're going to talk about F-tests and hypothesis testing for choosing between models, where we take into account how good it fits and how complex it is. And in the third video, we'll talk about model selection and more automated ways of choosing between models where we have a large set of candidate models. To illustrate what we mean by goodness of fit, let's just consider some toy data. So what I got here is 10 data points, okay, with an X variable and a Y variable. And the data points here are shown as black points. You've got a point here, here, etc. Okay, and there's a data point down here that's on top of the line. Okay, and then what I've done is fit the model of the form y is ax plus b. Y is well, let's say a plus bx plus epsilon. And we fit the model to find our estimate a hat and b hat, and that is what is shown by this dashed green line here. That is the line of best fit. The fitted values are these points shown in blue in the diagram, and these are the values we're going to call y hat, which is a hat plus b hat x. Okay. In other words, what the model predicts when we plug in the fitted values of the parameters a hat and b hat. And you can see all these blue points, these are the fitted values, these will all lie on the line. They're what the model predicts until they've got to lie somewhere on this straight line. The residuals here are the difference between the observations and the fitted values. So that is this distance here. So the residuals are epsilon hat, and that's the difference between the observation and the fitted value. So to judge how good a model is, or how well it fits the data, we can calculate how close the observations are to the regression line. So we usually calculate what is called the residual sum of squares. So we take all of these residuals, all of these distances, we square them all and add them all up, and that is the residual sum of squares. And of course we fit the model in the first place by minimizing this sum of squares, so we know that this line is the best possible single line that we could have drawn through these points in order to minimize these residuals. But of course we don't go through all the points, we still have some error left over, and that's called the residual sum of squares, and that gives us this term down at the bottom. One problem with using the residual sum of squares is that it is scale dependent. By which I mean is the scale that we've measured y in affects the answer. So if y was length of something, then it shouldn't make a difference whether we measure y in meters or millimeters. After all, millimeters are just the length in meters times by 1,000. But what we can see by looking at this expression for the residual sum of squares is that if we converted from meters to millimeters, we're going to multiply the residual sum of squares by 1,000 squared by 1,000,000. So the answer we get for the residual sum of squares is highly dependent upon the scale we use to fit y. So what we tend to do instead is convert the residual sum of squares to something called r squared, or also something called the coefficient of determination. So r squared is 1 minus the residual sum of squares divided by the total sum of squares. So the total sum of squares, we can think of it as just the variance of the data. It's this expression in the denominator here. Okay. Another way of thinking about that is it's the residual sum of squares if we fit a constant model. Okay. So if we fit a model that's just a horizontal line to data, okay, and would fit that, the best horizontal line we could fit would be at y bar. Okay. And then if we add up all the distances from this line to the data points, okay, and square them, that gives us this total sum of squares in the denominator, that's r squared. Okay. So r squared is 1 minus residual sum of squares over the total sum of squares. And we find that r squared always takes a value between 0 and 1. Okay. So the best possible value we can get is 1, or often we convert it to a percentage, multiply it by 100, so we get 100%. So for this data, these data, and this model, we have an r squared here of 0.58, or 58%, if you like. So the way we use r squared is to use to compare two models by comparing their r squared values. The model that has the bigger r squared value is doing better. Okay? And we think of r squared as the percentage of variance explained by the model. So in this case, we've got an r squared of 58%. So we say that the linear model explains 58% of the variance in the data. So let's now try improving our model. So we had a linear model before, so now let's make it more complicated and fit a quadratic model. Okay. So instead of the model y is a plus bx, I've now included a cx squared term to make it a quadratic model. Okay. And that gives me the green line shown here. Okay. So we've got new fitted values, these are the new points, blue points on this green line. Okay. And we've got a new r squared value of 62.8. That's better than the 58% we found for the linear model. Great, we've got a better model, at least if we measure it by the r squared value alone. So why not take it one step further? So instead of a quadratic model, we could have a cubic model. Okay, so I've got now a plus bx plus 6 squared plus a dx cubed term. I get a new fitted line, that's a new green line, okay, new fitted values. And now the r squared is improved to 63.1%. So we're doing even better, at least measured by r squared. Well, let's do it again. So we can have a quartic model. So I've got an ex to the 4 term, and it's now improved the r squared to 63.5%. So let's take this to the logical kind of extreme here, and we'll fit a 10th order model. So I've got an a plus bx plus 6 squared plus dot 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 all the way up to h x to the 10. Okay. So I've got 11 parameters in my model, I've got 11 data points, and now you can see the fitted line, which is still the green line, goes exactly through every single data point. So it's perfect in terms of fitting the data. Okay. And we've got an r squared value now of 100%, yeah, of 1. Okay, it's perfect in some sense. Well, what's the problem with this? Well, the problem with this is that it's vastly overfit. This model is essentially too complicated, it's too complex. We're not describing the signal anymore, we're just describing the noise in the data. To see that this model is useless, imagine you wanted to make a prediction about what y would be when we stepped out to 12. Okay. Which model would you like to use for prediction? Okay. You could use this 10th order model, which would give some value all the way down at minus 1,000 or whatever. Or you could use the linear model, which would give a value up here. Or you could use this quartic model, which would give a value down here, etc. Now, it's not an easy question to say which model would best for this. It's a matter of judgment to some extent. So an improved measure over the r squared is what is known as the adjusted r squared. So what we've essentially seen in the previous few slides is that a complex model will always fit the data better than a simpler one. We shouldn't rely on goodness of fit alone. We also have to take into account how complex a model is when choosing between models. So kind of the guiding principle in statistical modelling is that we want to choose the simplest model possible that adequately describes our data. So the adjusted R squared is related to R squared using this kind of rather complex formula over here. You don't need to remember these things. But essentially it takes R squared, okay, and it divides by something related to the number of parameters. Okay, so P is the number of parameters in the model and related to the complexity of the model. Now the idea is that adjusted R squared accounts for the complexity in the model. Okay. So what over here in this table is a list of R squared with the order of the model. Okay. So this was for linear models, this is for quadratic, etc. And we've got the R squared values we saw before. We've also got the adjusted R squared values. So you can see that although R squared increases if we go from a linear term to a quadratic model, the adjusted R squared goes down slightly. And it goes down even more when we go to the cubic models or the quartic models. Okay? By the time we get to that silly model where it goes through all the data points, we've essentially got an adjusted R squared of minus infinity. So the adjusted R squared value here tells us that the linear model, or the order 1 model, A plus BX, is the best model. Okay, it has an adjusted R squared of 55%, and all the more complex models have a lower value for the adjusted R squared. And so we should favour this model for making predictions and so on. So the main message from this video is that we can measure goodness of fit using things like the residual sum of squares, but in order to choose between models, we also have to take into account their complexity. In the next video, we'll look at how to do this in a statistical hypothesis testing framework.